All right, welcome to section 1.3 in differential equations. This particular section is important for a lot of reasons. One is it's very visual, so you get a good feel for what's going on with these differential equations. The thing that you see there on the right, y prime equals x plus y. The x plus y on the right is part of something called a slope field. A bunch of points in the plane which would have slopes. You could also think of it as you're in a river and you're looking at the way the current pattern is. The current is flowing often different at each point in the river. So f of x and y is x plus y. And so if you picked a particular point, that place in the plane would have a slope, namely the sum of the two coordinates. So minus 2 added to a minus 3, and I would have a slope at that particular point of minus 5. We need a tool to be able to generate a slope field. And if you look on the internet, there's probably a lot of different versions. The one I found that I kind of liked was this one that's here in the notes. And so let's take a look at that. So to start it off, this is how it looks. You put in what your slope field should look like. You can play with these numbers, but often we don't need it. We just need a rough idea. What does the flow field look like? Density, you can play with that. That's how many of these slopes are going to be on the graph. And the length is, well, how long do you want them to be? All right, so I did that for this particular function, and it tells you that. I also selected that I'd like to see different solutions. So what this solution is the following. If you picked, for example, point A here, which is 2 minus 1, that would be my initial condition for the differential equation. So I would have y at 2 equals minus 1. So what the flow field tells me is, well, right there, the slope of that line is 1. And so if I put a feather or something in the river and I watched how the feather would flow with the river, it would flow this particular way. And so you would see the way that the item would move in time. So now notice, if I picked a different initial condition, well, I have slightly different slopes and a slightly different flow pattern. If I picked a initial condition over here, notice the long-term behavior is very different than on the other side. So the flow field shows you what happens over time, and it also shows you how your differential equation depends highly on the initial conditions that you start with. All right, in question 2, the slope field is much harder to try to calculate by hand. They suggest you can pick x's and y's with these numbers. So my flow field is 2y minus 2 sine x. And so again, I went to my software tool. I put that in, didn't mess with anything else. Checked that I wanted to see various solutions. And so what we can see there is, again, depending upon your initial condition, The flow of your object is going to be very different if I start there versus if I start on this path. So if I started anywhere along this path, then this would be the trajectory I would take. So again, your flow field determines the long-term behavior and the path or trajectory of your particular item. All right, in question 3, we have a slightly different flow field. Depends upon the x and y coordinate along with this +2 on the end. And so the question is in the homework, well, which one of these is it? All right, well, which one of these is it? Again, I went to our tool to try to get a feel for what does this look like. And so 3y minus x plus 2. And so again, I'm looking at my various trajectories that would happen based upon my initial conditions. And again, different initial conditions make the flow pattern very different. See, if I started here, the question is, well, I might go this path or I might keep going. Really depends upon where your initial condition is located. All right, in question 4, similarly, except now we get some squares into the game. Makes the flow field look a bit more complicated, but again, just enter it into your software, look at some various patterns for what it looks like, and generate your flow. So let's just say, I don't know, I started here. Well, it looks like if I'm generating these 2 points, looks like I'm going to come down here. But right when I get to this point, look, the graph levels off and suddenly I'm turning. And then it looks like at some point after that, I would be going upward. So again, where you start all along this particular flow field, there is a slope, and the slope is generated by the item there on the right. Question 5 is kind of a technical situation, and it says that for our first order differential equation, y prime equals our flow field. That thing will have at least one solution if on the open interval around a particular point the function is continuous. It exists. And if the partial derivative near there is also continuous, then in that case your solution will be unique. All right, so the question is, given this situation, 1, does a solution exist, and is it unique? So, some of you may not have had Calculus 3 before. So let's start off with an example from Calculus 1. Supposing I change the problem, I get rid of the y, and I just have a 5 there. So f of x is square root of x minus 5. Square root function, I've got the graph there below. And when I plug in 5, I get 0. That's great. It is defined at 5. But what if I want to take the limit? If I take the limit from the left, meaning I'm coming in from the right, from the plus side. If I'm coming in from the plus side, then the graph would say I'm going to 0. But what if I come in from the other side, from underneath 5? Now from the graph it looks fine, but the problem is if I'm coming in from under 5, for example 4, 4 minus 5 is a negative 1. I've got the square root of a negative number, which is a complex number, and I can't have that. So the limit from the left doesn't exist. And for something to be continuous here in Calculus 1, I need the limit from the right to match the limit from the left so that the full limit exists. And I need, if that's the case, I need that to actually be equal to the function's value there for the function to be continuous at that point. In Calculus 3, there's a similar kind of deal. And with this function, there's a problem along the line y equals x. Similarly right here, when this was equal, x equaled 5. So a similar problem is going to happen along here when x is equal to y. And if you look at the graph here, here's the x-axis, the y-axis, the z-axis. All along this line, the function is 0. But if I picked points on this side, it's defined. But if I'm over here on this side, it would generate a complex number. And so if I'm on that particular line, then I'm not going to have another side. So at 5, 5 is 0, and it's not continuous there. Let me see if I can make this a little more sense. In Calculus 1, for something to be continuous, I had to have it go from the left and the right. And that was it. If I'm in higher dimensional calculus, to be continuous at this point, any path that I take to get there, any path, it can be the straight path, it can be a curvy winding path, but every path that I use to get there, I must get the same limit. So in our case, it's not continuous, so there's no condition that a solution would exist. In question 6, we have a much nicer looking function. We've got x cubed minus y to the 8th. Think of it as a polynomial with nice powers. So, being nice and a polynomial, it's going to be continuous everywhere for any point in R2. Any x, y that you pick. So yes, it will at least have a solution. There exists at least one. Could be more, but at least one. If I do this derivative of f with respect to y, this symbol means the partial derivative. It means think of all x's as constants or numbers. Everything else, the y's, are variables. So the partial derivative with respect to y of x cubed is 0. The derivative of this term is just like any old normal derivative. And so I would get minus 8y to the 7th. But again, this function is a nice polynomial looking thing. So therefore, it's going to be continuous on all of R2. Therefore, our problem has at least one solution. Now, since the partial derivative is also continuous, my solution is unique. All right, in question 7, we jump out of a helicopter and pull the ripcord of our parachute. Through trial and error, hopefully they didn't use real people, But the air resistance, the proportionality constant, is 1.64. So your downward velocity satisfies this particular differential equation. We're just falling out. We're not trying to jump faster, so my initial speed is 0. So the question is, what will your limiting velocity be as you fall from the airplane? What's the limiting velocity? No, it doesn't keep getting faster and faster and faster. Because of air resistance and this proportionality, you will hit a limiting velocity. Just like if you used a parachute from an airplane, there is a limiting velocity. So, how I did this problem, and we also want to know how long to reach our 95% of the limiting velocity. So to do this, I made a picture of the flow field. And the first thing I notice about this particular flow field is it's not all over the place. It seems to be our speed will increase, but after some time, all of these trajectories are flattening out. They are leveling off. Now, the dotted line or so is right about 20. All right, so we're not quite reaching 20. It's above 18, looks even above 19. So it's a little bit above 19. We'll call it and say it's approximately 20 feet per second. Now, in the next section, we're going to see that this differential equation is something called separable. So you can separate it, meaning I can take all the v stuff on the left. I can leave the 1 and dt on the right, and then I can integrate both sides. And so we could actually figure out what is the exact solution. I went ahead and cheated and I used Wolfram Alpha. So plugged it in, asked Wolfram Alpha to solve this for me. And it did, and it gave me that the exact solution, V of t, is given here that you can see. So as time goes on, this decaying exponential is going to 0, leaving you the number in the top. So the limiting velocity speed is 19.512. And so we could make a sketch of the flow field. We were noticing that it was leveling off. So you might say, well, A and B both look like they're leveling off, but we saw ours was leveling off around 20, and this one is leveling off around 30. And C and D clearly are not it. All right, so the last question then is, how long will it take us to get to 95% of our limiting velocity, which we said was about 20? Well, 95% of that is 19. And so looking at all my graphs, we're here at 19. So about how long is it going to take us to get there? Well, let's see. If I take my exact solution, all right, and so we're trying to figure out, okay, what would we get for 95% of my terminal velocity? See, I'm using the exact ones, not the 20. I'm using the 95% of the exact limiting number. I'm using the exact answer. And now I'm solving. And keep isolating till you get t by itself. And so when you calculate this, you get that t is around 2 seconds. So if we did this precisely, you would see that t is 1.82 about. All right, and that concludes section 1.3.